Welcome back, everyone, to Computer Science 150. Today's lecture is a continuation of what we started back on Monday. On Monday, we were looking at various algorithms to work with arrays, and one of the things that I introduced you to on Monday was a sorting algorithm that can be used to take a list of numbers and sort them into order. The first thing I want to talk about today is I want to go back and review briefly one of the things we did last time. And I also want to uh, talk a little bit more extensively about under what circumstances a solution to a problem is a good solution. All right, so what we have here on the screen is some of the code that I was showing last time. This is part of the code to solve the problem of taking a list of numbers and determining which number appears most often in the list. And near the end of the lecture last time, I proposed a solution to this problem that involved first taking the list and sorting it, and then once the list is in sorted order, finding the repeated numbers becomes much easier, because in a sorted list, the repeated numbers would show up as runs of the same number. And then all you have to do is do a search process to find the longest such run that you can locate. Right, so here again is the code that does that. What this code will do is it will start by reading a list of numbers from a text file. It will use the selection sort algorithm that I introduced you to on Monday to put those numbers into order. And then what follows is an algorithm that I described last time to basically scan down the list looking for the longest run of repeated numbers that you can find. Okay, now it turns out that the overall sort of effectiveness of this solution, as with many solutions, is limited by the part of the solution that takes the most work. And in this particular algorithm, the part of the solution that takes the most work is the step where we have to sort the numbers. Now, to give you a sense for what impact the sorting step has on things today, what we're going to be looking at today is we're going to be looking at a slightly more challenging version of this problem. And we're going to see how, as the problem gets more challenging, the sorting step has the potential for really bogging things down and slowing things down. All right, so here's the first thing that I'm going to do today. On Monday, when I first showed this example, I showed the example reading a fairly short list of numbers from a file. All right, well, that's going to change very dramatically today. The first significant change I've made is I've changed the structure of the data file that has the numbers in it. Two things are going to be happening now. One is that the numbers are now slightly larger, but the far more important consideration is that there now are vastly more of them. In fact, if you scroll all the way down to the bottom of this file to get a sense for how many numbers are actually here, what you'll see is that there's a large number of numbers in the file. There's exactly 200,000 numbers in this file. All right, so what we're dealing with here is the exact same problem as before. Once again, it's the same problem. Figure out which of these numbers appears most often. The only thing that has changed is that the scale of the problem has grown significantly. On Monday, when I showed you the input file, it had about 10 numbers in it. This file, on the other hand, has 200,000 numbers in it. So that means we have greatly increased the scale of the problem that we're working on. Specifically, we're now dealing with 20,000 times as much data as we had in the example on Monday. Right now, an important question to ask in computer science is, if you've written a solution to a problem and it seems to work reasonably well for a small data set, how is the problem going to react when we give it a much larger data set? So in this case, we're shifting from a small data set to a much larger data set, which is literally 20,000 times bigger than the original data set. Now, a question you might ask related to that is, it's clear that if we have more data that needs to be processed, it's clearly going to take the algorithm longer to process it. Now, most people, if you ask them, if I gave the same algorithm 20,000 times as much data, how much longer do you think it would take the algorithm to run? Most people would guess that if you have 20,000 times as much data, it's going to take 20,000 times as long for the algorithm to process that data. That's a reasonable guess, but unfortunately for most algorithms, that original reasonable guess is wrong. And let me now explain why. The actual increase in time to process data is related to what's called the scaling behavior of some of the parts of your algorithm. And once again, in this particular algorithm, the culprit is going to turn out to be selection sort, because selection sort, it turns out, has the worst scaling behavior of any part of this algorithm. Right? So again, you might think that if selection sort can sort a list of numbers in a certain amount of time, if you then throw, say, 100 times as many numbers at it, it would take 100 times as long for it to sort that larger set. Right? Well, that turns out not to be the case. In fact, the scaling behavior for selection sort is much worse than that. And we can get a sense for that by taking a closer look at what selection sort does and make some quick sort of back of the envelope estimates of how much work it would actually take selection sort to sort the list of numbers. Right, so to see this, the first thing we need to notice is that selection sort is basically a pair of loops. There is an outer loop and there is an inner loop. One thing you can immediately tell from looking at the outer loop is that it goes around as many times as you have numbers in your list. Right, so one effect this is going to have is that if we are sorting a list that has n numbers in it, that outer loop is going to go around for a total of n iterations. Right, now worse yet, on each trip through the outer loop, we're also going to have to do another loop, which is this inner loop. All right, now this inner loop is a little bit harder to predict because what this inner loop essentially ends up doing is it ends up covering only part of the list. Specifically, what it does is it covers the unsorted part of the list. And on average, averaged over the entire behavior of this sorting algorithm, on average, the unsorted part of the list is going to be about roughly half of the list. Okay, so on average, if you have n numbers in your list, this inner loop is going to have to go around about n over 2 times. Now, what kills you is when you multiply both of these factors together. You have an outer loop that is going around n times, and on each trip through the outer loop, you have an inner loop that's going around roughly n over 2 times. So if you ask, what's the total amount of work going on here? It's the product of those two factors. So what that tells you is that if you have a list with n data items in it, it's going to take roughly n squared over 2 operations to do the sorting. Right, now, this is really bad news because this tells us that the scaling behavior of selection sort is actually quadratic. And for example, one consequence of that is if you time selection sort on a particular list, and then you come back and you hand it a list which is 10 times as long, it's not going to take selection sort 10 times as long to sort the longer list. It's going to take it 100 times as long, right? Because the amount of work that selection sort does is proportional to the square of how many things you are working with. Okay, now that has the potential to really kill us in this example, because in the first version of the problem that we were doing, we were working with a list that had 10 items in it. This time around, we're working with a list that has 200,000 items in it, or roughly 20,000 times as big as the original list. And since the amount of effort that selection sort takes is proportional to the square of how many data items you have, if you have a list that is 20,000 times as long, it's going to take it 400 million times as long as it would have taken to sort the original list. Okay, now let that sink in. That is hugely dramatic. So when we go from 10 items in a list to 200,000, if we could time how long it took the algorithm to process those 10 items, it's going to take it roughly 400 million times longer to do the longer list. All right, now that seems impossibly long. That seems incredibly long. But one of the other things happening here, which will work to our advantage, is that modern computers are very fast. For example, if you run selection sort on a list with 10 items, most modern computers can do that sorting in about a tiny fraction of a millionth of a second. It's a very, very short span of time to do the short list. So that helps, because if the longer list is going to take you 400 million times as long, you're basically scaling up from a tiny fraction of a millionth of a second, probably up to several seconds, anywhere from 20 seconds to 200 seconds. It's hard to predict, but it's going to be of that rough order of magnitude. Okay, well, let's not guess any longer. Let's actually run this thing and see how long it takes to actually figure out what is the most common number in the list of 200,000 numbers. I'm going to go ahead and start this thing running, and we'll get a quick sense for how long it takes. Okay, so there's our answer. It took probably about 15, 20 seconds. And it determines that the number 875 is the number that happens to show up most often. It shows up 249 times in the file. So despite the terrible scaling behavior here, where this one took 400 million times longer than the simple problem, it's still reasonable because modern computers are extremely fast. Right. However, having said that, this is sort of the upper bound of what we can get away with, because this scaling behavior is going to continue to hurt us. For example, if we now switched from an example where we went from 200,000 numbers to a million numbers is 5 times as large as this data set. And since the scaling behavior is quadratic, that means that this algorithm would actually take 25 times longer than what we just saw here. All right, so if we had something that took about 15 seconds, that's about a quarter of a minute, and you scale it up by a factor of 25, it is now going to take about 6 or 7 minutes to process a million items. Right, and things only get worse beyond that point, because again, the scaling behavior here is quadratic, very poor scaling behavior. Okay, now in a minute, what I'm going to do is I'm going to try to find a way to make this whole algorithm more efficient. But before I do that, does anybody want to ask any quick questions about what just happened in the example here, and the explanation about the scaling behavior of why it takes a quadratic scaling behavior here? Okay, well, if not, let's now, oh, sorry, here's a question.
Yeah, can you briefly explain selection sort again, like what it means?
Well, again, the basic behavior of selection sort, I covered that in the lecture on Monday. And what I would do is refer you back to that lecture. And also there's a discussion of selection sort in the book in chapter 7. Again, the main thing that I wanted to point out about selection sort here today is its structure. It's basically a pair of loops. The outer loop is basically going to essentially add one new number at a time to the sorted part of the list. But then to do each of those numbers, it takes extra processing, because for each new number you add to the sorted part of the list, you have to scan the unsorted part of the list, and that inner loop is going to take work to do that.
All right, thank you.
Other questions here?
Yeah, I got a question. Just a quick thing. In line 60, it says current bin index exclamation point equals I. What's the exclamation point doing?
That is not equal to I. That's basically a check, because we're about to make two numbers trade places, and that check is just checking to see if those numbers are in the same place, because if they are, they don't need to be swapped.
Okay, cool.
Okay, so that was selection sort. And again, the big problem with selection sort is that as sorting algorithms go, it is relatively inefficient. And the worst thing about selection sort is it exhibits this quadratic scaling behavior. If you scale up the size of the list by a factor of 10, selection sort is going to take 100 times longer to sort it. And that's very bad behavior. Okay, so what we're going to be doing in the rest of the lecture today is we're going to be working on replacing selection sort with a better sorting algorithm, specifically a better sorting algorithm that has a more has better scaling behavior and will allow us to solve this problem more quickly. Okay, now, the first thing I want to talk about in introducing you to this better sorting algorithm is that this improved sorting algorithm is going to make use of an essential step. And the first thing I want to talk about is this so-called merge step. All right, now this is actually interesting in and of itself because this solves a problem that you may occasionally need to solve outside of the context of trying to sort lists of numbers. All right, so here's the problem that this merge method is solving. It's working with 3 separate lists, and the assumption here is that the first 2 lists are already have numbers in them, and we're also going to operate under the assumption that the numbers in the first 2 lists have already been sorted for my benefit. Right now, the job that I have to do here is, because I have 2 separate lists of numbers, what I would like to do is merge them together into a single larger list, and that is this 3rd array that we're working with, the so-called destination array. All right, so what we're about to see here is an algorithm that can take 2 lists of numbers that are already sorted separately and merge them together into a larger list that contains all of the numbers, but again, in sorted order. All right, so here now is the algorithm to do this. The algorithm is going to be making use of 3 index variables, and the purpose of these index variables is to keep track of separate locations in each of the 3 lists. I is basically going to keep track of where we are in list 1. J will keep track of where we are in list 2, and K will keep track of where we are in the destination list. And we start at the beginning of all 3 of these lists, so all 3 of those indices are set equal to 0. Okay, now most of the work in the algorithm takes place in this loop, and the purpose of this loop is to basically keep running as long as numbers are still available in the 2 lists that we're trying to merge together, right? So that's what controls the test for the loop. The test basically says, as long as we have not fallen off the end of the first list and we have not fallen off the end of the second list and we still have numbers available to work with, let's work with the 2 numbers that we're currently looking at. There'll be one number that sits at location I in the first list, and there'll be a second number that sits at location J in the second list, right? So what we're going to be doing is looking at the number at location I in list 1 and the number at location J in list 2. All right, now what we're going to be doing is we're going to be picking one of those 2 numbers and moving it over to the destination list. And the correct number to pick for this purpose is the smaller of those 2 numbers. All right, so we have a test here that's trying to determine which of those 2 numbers is smaller. Is the number from list 1 smaller, or is the number from list 2 smaller? All right, so once we've determined which of those 2 numbers is the smaller one, what we do next is we move that over to the destination list. All right, so that looks like this. If 1 is the smaller number, we copy it over to the destination list, and we increase these 2 indices because we're going to be moving on to the next location in the destination list, and we're going to be moving on to the next location in list 1. The other possibility is that the number from list 2 is the smaller of those 2 numbers. In that case, it's the one that gets copied over to the destination list, and if we copy that one over, we increase these 2 indices in that way. All right, and we just simply continue that process. We go around for a number of rounds, and on each round, we take the smallest available number from the 2 lists and we move it over to the destination list. And that is guaranteed to do most of what needs to be done here. All right, now, the only remaining thing we need to worry about is this loop here will stop as soon as we run out of numbers from either one of the 2 lists. So what we have to do after finishing the main loop is we have to come back and check to see if there are any numbers left in either of the 2 lists that haven't been moved over yet. All right, so we have one loop here that is basically going to keep moving numbers over from list number 1 until there are no more numbers left in that list. All right, and all that simply does is it moves the numbers one at a time from 1 to the destination list and goes on to the next available number. Likewise, there's a separate loop here that will move any numbers over that may still be stuck in list number 2 It gets them moved over to the destination. And when we're done, all of the numbers from the original two lists will have been copied over to the destination, and we will have correctly merged the two lists together into our destination list. All right, so let me pause here and ask if anybody has any questions about how the merging idea works.
I have a
Okay,
question.
so a question here. Mhm.
Yeah, so I guess this isn't really exactly about the merge, but how you're writing like the K or I or J and then the plus plus, is that the same as doing like K equals K plus 1?
Yeah, and in fact,
Okay.
very often when we're dealing with indices that are being used as indices in an array, if you have to increase an index by 1, this is by far the most common way to do it. But you're right, you could also write instead K equals K plus 1, and it would do the same thing.
Thank you.
Mhm. Okay, so this is the merging algorithm, and it's interesting in and of itself because occasionally you'll have to merge two lists together. So here's some code that will do that. More questions here before I go on?
Yeah, I just have a quick question. What would happen if you change the line 60 from and to or? So is there a way to like, just merge the two sections? I mean the top section where
Yeah,
you do
this
the,
is
yeah.
an important question to ask because whenever you're writing a test for a loop, it's always important to ask, did I get the test right? Right now, one way to think about this is that the test in a while loop is always asking the question, under what circumstances should I keep doing what I'm doing? And the answer in this case is that you should keep doing what you're doing as long as both lists still have numbers in them. And since this talks about a situation where both lists have numbers in them, that would require an and. On the other hand, if we're talking about a situation where you want to keep going where either of the two lists has something left in it, that would require an or. Right. Now, in this case, the correct version is the both. We want to keep doing the main loop as long as both lists have numbers available for us to look at, because on each round, we're going to be looking at numbers that come from both lists. And that process only makes sense and can only continue as long as both lists still have numbers available. Right? So that's why it's both, and both requires us to use an and here.
What I mean is, since you are moving the remaining of the list that has a larger number or more numbers in the list, why don't we just do it all at once?
Well, again, it's hard to predict in any given example which of the two lists is going to run out of numbers first. So we basically let the main loop run until somebody runs out of numbers. And as soon as either one of these runs out of numbers, we'll drop out of the main loop. And then, since we can't predict which of the two lists ran out of numbers, we simply write code that looks at both of them. And what will happen here is, suppose list number 1 was the one that ran out of numbers. In that case, I would already be equal to the length of list 1. That would cause this test to immediately fail, and that would basically end up doing nothing with list number 1. But we have to ask anyway, because even if number 1 has run out of numbers, we have to ask anyway, because there may still be the possibility that list number 1 has some numbers remaining. And we have to ask that question for both lists, because we can't predict which of the two lists is going to run out of numbers first. And because we can't predict that, we have to check both of them separately.
So can I say if, well, since you cannot predict, so what if we change the first section from and to or? So regardless of which list is longer, you'll always have some number to move over to the destination. And then maybe you change the if test from less than to more than. So like you're always gonna move the, I or J, which either one is bigger.
As you'll learn, as you start tinkering with this, and as soon as you start changing some of the key details, about the only thing that does is it makes your life more difficult. Yeah, so if you'd like to sort of on your own time tinker around with this, I have posted all of the code for today's lecture on the course website, so you're welcome to download that and tinker around with this and try alternatives. And what you'll find in virtually every case is that if you make any change to what we've got here, it's more than likely going to end up breaking the algorithm in some significant way.
All right, thank you.
Mhm. Okay, so now the reason that I'm showing you merge today is that merge plays a larger role, and that is merge plays an essential step in another sorting algorithm. And the next sorting algorithm that we're going to look at today is an algorithm called merge sort. And it's called merge sort because one of the essential steps in merge sort is this merging process that I just showed you. Okay, now let me say a few words about how merge sort operates. Merge sort is a more sophisticated sorting algorithm than selection sort, and it relies on a more sophisticated strategy for sorting a list of numbers. The main thing that you can say about merge sort is that merge sort uses a problem-solving strategy called the divide and conquer strategy. And in a typical divide and conquer strategy, if you have a block of data that needs to be processed, you say one strategy for processing it is cutting the data exactly in half and then going off and working separately on the two halves and then somehow combining the two halves together. That is exactly the strategy that merge sort uses. Right, so here's what it will do. If you give it a list of numbers that need to be sorted, the first thing it will do is it will break that list of numbers into two halves. And for that purpose, it's going to create a couple of arrays. One of these is half the length of a list. The other one is also half the length of a list. And each of these two half arrays are going to end up getting copies of half of the original data. Right, so that's the divide part. We take the original list and we divide it into two smaller lists, each of which has exactly half of the available numbers. All right, then the next step is once you've split the list into two smaller lists, is we then process those two lists separately by sorting them separately. So what we have here is two method calls that are going to be sorting the two shorter lists. And once those two method calls are done, those two lists will each be separately sorted. Right now, at this point, we want to take advantage of the merge code that we just developed because what we have in that merge method is a piece of code that can take two smaller lists, both of which are sorted, and merge them together into a larger list, which is also sorted. And once we've done that, we've finished our work. We basically have figured out a way to sort the larger list by breaking it into two smaller lists, sorting those two lists separately, and then merging them back together to get the final thing done. Okay, now one aspect of this seems a little bit crazy because this is going to involve doing something that you've never seen before. One slightly weird thing that this method does is as part of its work, it actually ends up calling itself. Right? Now, this is a thing that we've never encountered in programming before, but it's a perfectly valid strategy that's frequently used in programming. This strategy even goes by a fancy name. It's called recursion. We say that an algorithm is recursive if it ends up calling itself in an effort to solve a particular problem. Right? And that's essentially the strategy that merge sort uses. It takes the list, breaks it into two smaller lists, then sends those two lists back to itself to be sorted, and then it does the merging step to recombine them. Right now, since this is the first time you've ever seen a method that calls itself, this does seem slightly weird, but this actually turns out to be a perfectly legitimate thing to do. It is actually okay for a method to call itself. The only thing you have to watch out for when you're doing this sort of thing is you have to watch out for the possibility of what's called an infinite regress or an infinite recursion. Because if merge sort ends up calling itself, and the merge sort that you're calling here also ends up calling itself, you're in danger of setting up a situation where you end up going around in circles an infinite number of times. This is always a problem that you could run into when you have a method that calls itself. It could simply end up calling itself an infinite number of times and in the process never getting anywhere. All right, well, that is something to worry about. But there's always a strategy for dealing with that, and that is to make sure that that process doesn't continue indefinitely. All right, and here's how we're going to manage that. One thing we can count on here is that each time somebody hands us a list, the first thing we're going to be doing is making the list smaller. We're going to break it into 2 smaller parts, each of which are half the length of the original. So that means when merge sort calls itself, it will be calling itself with a shorter list. In fact, every time it goes around this circle and calls itself again, the list is going to keep getting shorter and shorter. Now, eventually, when the list gets short enough, we can stop the process. And the way we do that is by adding some extra logic to the code that basically checks to see if the list has gotten sufficiently short. So we have an if statement right at the very beginning that checks for that situation. It checks for the situation where we have divided the list so many times that the list now is very small. It's now shorter than 20 items. And when we get down to that point, we're going to stop subdividing the list any further. We're simply going to stop and say, okay, I need to sort this list. Let me sort of cheat and ask somebody else for help with that. I'm going to use the old selection sort algorithm to sort that shorter list for me, and that will stop the process whereby merge sort calls itself. Because eventually, when merge sort calls itself on a list that is small enough, we're simply going to stop doing that and hand the problem over to selection sort, and selection sort will finish doing the work of sorting that very small list. Okay, so this is a mind-bendingly weird algorithm. This is by far the strangest thing we've encountered so far. And about the only thing I can say at this point is, trust me, this actually works. This idea of dividing the list into 2 halves and then calling yourself to do the sorting on the 2 halves and then merging the 2 halves together, it actually works. It's an effective algorithm for sorting numbers. And better yet, not only does this work, but it's extremely efficient in doing its work. One of the hallmarks of these divide and conquer strategies is they tend to be very efficient algorithms, and they tend to have very good scaling behavior. In fact, the scaling behavior for this merge sort algorithm is if you give it a list with n items in it, the amount of time it will take to sort that list is proportional to n times the log of n. And that is much, much better than the n squared that you get from selection sort. All right, so that's one of the big selling points of merge sort. It is very fast and very efficient. All right, and to demonstrate this, what I'm going to have this program do now is I'm going to have it read this large list of 200,000 numbers. It's going to sort them, and then it's going to proceed to print them out. All right, now watch how quickly this works. I'm going to scroll up to the top here and then also give a little bit more space in the output pages to watch the output come out. Let's go ahead and run this thing and see how quickly it starts spitting out numbers. Okay, so there it is. In fact, the short delay there was it basically sorting the list of numbers. The only thing that actually took time here was simply printing those numbers. It turns out that merge sort was able to sort those 200,000 numbers in a tiny fraction of a second. And then most of the time that it took here was just simply the time that it physically took to print those 200,000 numbers out to the output pane. All right, so merge sort is a vastly more efficient sorting algorithm than selection sort. So going forward, especially if we have to sort a very large list of numbers, merge sort is going to be doing the work for us going forward because it's vastly more efficient and it's much faster than selection sort. Okay, so let me pause here and ask for questions. Anybody want to ask any questions about how merge sort works and sort of how it's doing what it's doing? Okay, well, let's move on to an application of merge sort. A minute ago, I showed you us using selection sort to answer the question, what is the most common number in a list of numbers? And as I pointed out previously, the problem with that first solution is that because it relies on selection sort to do the sorting step, selection sort really bogs it down. right? So the obvious next thing to do is to write a version of this solution that solves the same problem, but this time we're going to swap out the sorting algorithm, right? So all that I've done here is I've taken selection sort, which is very inefficient, and replaced it with merge sort, which is very efficient. And so now we're going to solve the problem again by sorting the list of numbers and then looking through that list of numbers for runs, seeing which run is the longest, and now we can get a sense for how much faster this is going to go. All right, so we'll start it running, and boom, there's the answer. Tiny fraction of a second figures out that once again, the most common number is 875. It shows up 249 times, and that ran absurdly fast, mostly due to the fact that merge sort now is absurdly fast. It's extremely efficient, and it gives you a very, very fast way to sort a list of numbers. So questions here?
I got a question. So when you switch to the second program here, fast most common, you have to move, like copy and paste all the info from merge sort into this one. Is there like any way to like call a different program from one program? Is that a thing that can happen?
There is a way to do that. In fact, let me show you how we could potentially do that. So a minute ago, I showed you this file. It was mergesort.java. Now that had merge sort already in it, and more specifically, that merge sort was a method sitting in this class here. Okay, now here is a way that I could avoid having to copy all of that sorting code over to the other program. What I could instead do is call the merge sort from the other program. And here's how you do that. I just saw that there is a method merge sort that is available in the class named merge sort. So all I simply have to do is reach over to that other class and say, hey, I'd like to use your merge sort algorithm. All right, and that basically would save you from having to copy the merge sort code from one class to another. You simply reach across to that other class and say, hey, I'd like to call your merge sort algorithm. Can I do that? All right, so that would be a way to save you from having to copy and paste all of the sorting code over from one class to another.
Oh, okay, cool, thank you.
And there was another question here. Anything else about this? Okay, and in fact, while we're on the subject of using handy methods that other classes provide to you, there is another class that we could have actually made use of in this example, and that is there's a class called the arrays class. To use it, you have to have an import statement. You have to import java.util.arrays. And one of the things going on in the arrays class is that the arrays class is provided with a bunch of useful methods to do useful things with arrays. And one of the things that you'll find in that arrays class is a handy sorting algorithm. It's called simply sort. And if you want to use it, you simply mention the arrays class and say, I'd like to use the sort method that's available in that class. Can I get that thing to sort my numbers for me? Right, now this turns out to be even better than using merge sort, because the sort algorithm that is available in the arrays class is an even more sophisticated algorithm. It's even faster than merge sort. So this would give us yet again an even faster way to do this. And again, it's hard to tell the difference between the two versions because merge sort is already pretty quick. And when we replace it with the sort method from the arrays class, it would be even faster in solving this particular problem. Okay, so going forward, from this point forward, anytime we come across the need to sort anything, we have now some nice resources for doing that. We can either use the merge sort code that I've shown you, or you could bypass that and go directly to the arrays class and use its sorting algorithm. Both of them are extremely efficient and very fast. So going forward, anytime we find the need to sort a list of numbers, we will go ahead and take advantage of those things. Okay, we've got about 5 minutes left, and in the 5 minutes that remain, I want to show you one further consequence of this merging code that we are looking at. It turns out that the merging code that I showed you as part of merge sort is useful for more than just what I demonstrated here. There are other kinds of things that you could use this merging logic for. All right, and as my final example today, I brought along an example of a completely different problem. The problem in this example is we're going to be working with two separate lists. I have two separate files with two separate lists. Neither of these lists are sorted initially, so they'll have to be sorted, and for that I'll be using the arrays.sort procedure. Now, after those two lists are sorted, I'd like to answer a question, and the question is, what numbers do these two lists have in common? In other words, what is the intersection of those two lists? All right, well, it turns out that computing an intersection of two lists is something that the merging code can do if you just make a few small modifications to the merging code. All right, so what we have here is a method that will take two lists as its input. It will generate a third list as its output, which is basically the intersection of those two lists, and it's going to use some logic similar to the merging logic to build that intersection. All right, and here's how it works. It has a main loop that, like the merging code, it keeps running as long as numbers are available in both of the lists. And then on each round, what it's going to be looking for is numbers that these two lists have in common. So on each round, the first question it asks is the number from list 1 the same as the number from list 2? Because whenever we find two numbers that are the same, they're going to be in the intersection, they're going to be interesting to us, and what we want to do is copy those numbers over to the temporary list. All right, so whenever I find two numbers that are the same, I'll make a copy into the temporary list and also move all of the indices along to the next numbers. Right now, if those two numbers are not the same, what I want to do next is I want to move past the smaller of those two numbers. So if the number from list 1 is the smaller of the two numbers, I'm going to move past that. Otherwise, I'm going to move past that because it turns out if the numbers are not the same, you basically need to throw away the smaller of the two numbers and ignore it because it has no chance of being in the intersection. All right, so regardless of what happens here, on each round, we're going to make some progress. We're going to work through the two lists. And then when we're done with the two lists, we'll know exactly how many numbers we've copied over because we have an index that we're using into the temporary list. And the value of that number will tell us how many numbers we copied over. All right, so the last thing I want to do is I want to make a final list here which has exactly the right length, that has as many numbers in it as we found in the intersection. And then I will simply copy the numbers over from the temporary list into the result list and return that. That now has found the intersection of those two lists. All right, and again, because it is based on a fairly simple merging strategy and using efficient algorithms for sorting things, this thing is extremely fast. The two lists that we're working with, here's list number 1. It has quite a few numbers in it. Let's see how many numbers it has. It has 100,000 numbers. I'm sorry, it's less dramatic than that. It's only 10,000 numbers. And list number 2, I think, is similar in size. It also, I think, has 10,000 numbers. But again, to find the intersections of those two lists of 10,000 numbers here is not terribly hard. If we just run this, it will find the intersection and print the numbers in the intersection. And again, it takes a tiny fraction of a second to do all of that. Okay, so that's the last of today's examples. Where we are now is this is also the end for the time being of my talking about arrays, because what's going to happen next is next week we're going to have a lab based on arrays. And also next week, we're going to be having our midterm exam. That's going to be happening in the middle of next week. So what I'm going to be doing on Friday is I'm going to be doing a little bit of review. I'm going to be talking about what to expect on the midterm exam and how to prepare for it. So we'll be doing a little bit of review material on Monday, and that's what's coming on Friday, and that's what's coming next. Okay, so until then, have a good day, and we'll see you all back either Thursday or Friday.
Thank you.
Welcome.